Good morning, everybody. And welcome, I guess this is the second welcome to the Deep Spec Summer School 2018 edition. We are delighted to have you all here. We are super excited about the material that we have to share with you. And the next few days are going to be getting you launched on a lunar trajectory to get you started for your stellar trajectory that's going to be the next 2 weeks. The book that we're going to be covering in these 3 days is almost all of Volume 1 of the Software Foundations series. Software Foundations used to be a single book. As part of the Deep Spec project, we've been greatly expanding it. It now has actually 5 volumes. You'll see 3 volumes on the public webpage of Software Foundations, but in your secret copy of the most up-to-date version of the book in the DSSS 18 repo, you will find the other 2 volumes and better versions of volumes 1 and 2 and 3. So those are the ones you should be referring to this week. Before we dive in, I would like to get a sense of who's in the room. So let's see. How many people here are from the United States? Okay, quite a few. How many people are from Europe? Almost as many. How many people are from other parts of the world, not those two? Ah, excellent. So we have about a 30-30-30 split. That's great. How many people here have already finished their PhDs and are working as postdocs or researchers or professors? Ish. Okay, a few people aren't sure. That happens, those of you that haven't been through that process. And how many people are working on their PhDs now? Okay, and some people are not sure. That also happens. And how many people are not yet working on their PhDs, but maybe they will later on? Okay, so again, a pretty even split. Not quite so many people that are finished with PhDs, but quite an even split of undergraduates, graduate students. This is great. Now let me ask the hard question. We recommended beforehand that everybody try to finish as much of the material in the first, I think, some places it said 4, and some places it said 3 or 4 chapters of the first volume of Software Foundations. How many people feel completely confident that they have mastered and internalized all of the material in the first 4 chapters? That is basics, induction, lists, and polymorphism. Now raise your hand high if you feel confident about all of that material. Excellent. Thank you. How many people feel quite confident about the first 3 chapters? Okay, very many people. Good. I'm not going to ask about the other 2 chapters. There are probably some people that are just diving in for one reason or another. We will catch you up to speed as fast as possible. But I am going to be aiming the lectures at the people that have already done some work in the first 2 chapters, so you will need to scramble to catch up. My goal for this morning, my goal for the first lecture of this morning, we have 2 lectures this morning by me. The goal for the first lecture is to go very quickly through the first 3 chapters, all in 1 hour and a half. So I will not really be lecturing about those chapters. I will be scanning through my slides for those chapters simply to remind you what's in them and give you a chance to ask questions. When I lecture about this material in semester-long courses, I assume that the people in the class are a little bit shy and tentative, and we use some software called Poll Everywhere that's really great for, let me see if I can get this working while I'm talking. When I lecture about this material to tender pen students, I usually use a software that allows people to anonymously answer. If I ask a question, then people can give the answer on their phone, and it's all very anonymous, and only the aggregate is displayed on the screen. And that's a way of making it very interactive without putting people on the spot. here, I don't want to take the time to get all of that set up. And anyway, I trust that you are all adventurous go-getters who have gotten yourself to an exciting summer school all by yourselves. So I'm going to just expect that everyone will jump in and participate and raise your hand and ask questions if you don't, if I say something silly or something doesn't make sense or something does make sense but you have a further question. Yeah. And we will all have fun together. So that's my request to you, is participate. These lectures are much more fun if it's more than just the three people in the front row asking questions. So let's go straight in. The first chapter of Software Foundations is called Basics. It really should be called something other than Basics because, as some of you have noticed, there's a file called Basics in the Coq Standard Library, and things often get really confused with search paths. If I had had one more day to prepare, I would have changed the name of this file to avoid that. Hopefully, everybody has gotten through that little bit of hassle for themselves. I think actually things have even changed in the way it works between Coq 8.7 and Coq 8.8, so I was having trouble with it just today. But like you, I hope, I figured it out, or I can tell you what to do. Okay, so here we are in the Basics chapter. And as you know, Coq is a proof assistant. It's an environment for stating and proving precise claims about artifacts that we define. So the artifacts that we define are, in general, programs. They're functional programs in a little functional programming language called Galena. Not too different from most other functional programming languages, except in a few respects. So it has a much more powerful type system. In fact, it has a much, much, much more powerful type system than most functional languages. Maybe with the exception of Haskell, I'm not sure. And it has a few restrictions that make it useful in a logical setting. In particular, it has this funny restriction that all function definitions must terminate on all arguments. So there's no unbounded general recursion in Coq, only terminating functions, and sometimes that gets in the way a little bit. There are various tricks that people use to get around it. But mostly, programming in Coq feels like programming in the purely functional subset of OCaml or Haskell. By the way, how many people in the room are already OCaml programmers? And how many are already Haskell programmers? Wow. Okay, and how many are already programmers in some other functional language? And how many are not familiar with programming in any functional language at all? Okay, a few. So this will be your introduction. So then I should say it the other way around. All these other languages are pretty much like programming in the functional language in Coq, only with tiny differences. In terms of syntax, the functional language in Coq, it's called Galena, is most similar to OCaml for sociological reasons. Okay, so in Coq's functional language Galena, we can define data types, and like every functional language, Coq comes with a whole bunch of data types built into the language or the standard libraries. We're going to ignore that fact and build all of them up from scratch, just for fun to see how it's done. So we can define so-called inductive types that are just enumerations of a bunch of constructors. And we can define functions over those inductive types by pattern matching. We can instruct Coq to compute with those functions. And here we're doing computation internally inside of Coq. We can also, and this is a whole story that we're not really going to go into, at least this week very much, but Coq has facilities for extracting functional programs written in Galena into other programming languages like OCaml and Haskell, from which they can be compiled with the industrial strength compilers in those languages, linked with libraries in those languages, et cetera. So you can actually write programs in Galena that do things like serve web pages. But that is not the main story, at least of the next couple of days. So for the next couple of days, we're living within Coq and simply asking it to simplify expressions. And that's what this compute keyword does. The other way of talking about computations is to state theorems about them. And the keyword example is actually a synonym for the keyword theorem and the keyword lemma and the keyword fact. So we give one of those keywords, we give a name to the thing in case we want to use it later, and then we state what we think is a fact. In this case, it's a fact about equality between two computations. This is a kind of trivial computation. This one actually involves some simplification. And here is the proof of that fact as instructions to Coq to do some simplification, and then notice that the two sides of an equality are the same. Okay. We can define other enumerated types like the familiar Booleans, and functions over those like negation. We can define multi-argument functions like and or. We can define notations for things that we previously defined that introduce, say, infix symbolic syntax for and or. And this makes programming in Coq a little bit more, a little bit easier on the eyes, a little bit more familiar from other functional languages. When we come to exercises, I'm sure you've all, or at least most, encountered this. When we come to exercises, they are invitations to replace, to throw away the keyword admitted, which in the files that we distribute to you is there to tell Coq, please keep processing even though this proof isn't finished, and allow you to fill it in and end it with QED, which means this is terminating the proof which should be finished at this point. By the way, the files that we distribute also include so-called tester files, and there isn't really any strong need for you to use them. We use them mainly in courses where we're grading homework assignments based on software foundations. We use the test files to do the grading ourselves automatically on the things that students submit. And we find it convenient to also distribute them so that the students can check their own work and just make sure that they're seeing the grade that they're going to get from us. But those tester files are not really doing anything else except making sure that all of the admitteds for the recommended exercises have been replaced by proofs plus QEDs. So we don't really need them here. Okay, we can define not only data, but we can define, excuse me, back up. We have defined data and functions. Coq, being a functional language, considers that functions are first-class citizens. That is, functions can be used as data, passed around, stored in data structures, and so on. And since Coq is a statically typed functional language, those functions as data have types just like everything else. And those types look like something arrow something. So neg B has type bool arrow bool. And if you type in check neg B, it will come back with bool arrow bool. Okay, we can build up data types from previously defined data types. So here's a silly example where we define the type of red, green, and blue, primary colors, and then we define another data type of colors where a color is either black or white or a primary color. And the fact that primary is a constructor taking a color as an argument is encoded in its type, which is an arrow type from RGB to color. So each of these declarations, where we say inductive blah, 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 is defining a set. So, so here's the model. In Coq's view of the world, there are already, at the beginning of time from nothing, all of the data values that you might imagine. And you can think of them as either trees of constructors or functions, functional values. Some of those trees have types, others do not. So when we give an inductive definition, we're carving out a subset of those trees and or functions. Sorry, let's forget about the functions. We're carving out a subset of those trees and saying these are the ones that belong to this type. So you should think of the constructors and the ways of putting things together as existing before the types, and the inductive definitions as carving out a subset. So what subset does it carve out? Well, this one is easy. It carves out the subset containing those three constructors applied to no arguments, and that's it. This one is a little bit more interesting. It says the things in this type are the constructor black, the constructor white, and anything that you can get by applying the constructor primary to something that's in that set. And only those things. That's the final bit of the force of the inductive keyword, is it says, here are some trees, let's give a name to those, and let's say that the only things described by that name are the things that we just defined. The reason that that's important and worth emphasizing is that it gives rise to reasoning principles, because now you can say, if something was in that set, if something is in the set RGB, then it must be one of these three things, because those were the only possibilities I said. Okay, we define functions on these things by pattern matching. The new bit that we're introducing here is that patterns can contain variables. Here we're not using the variable on the right-hand side, but we can. And we do in the definition on the bottom. And we can also use the underscore character as a substitute for a pattern variable in the case where we weren't going to use the pattern variable anyway. Okay. You will see module declarations around the place. Coq has a rather powerful and interesting module system. It's based on the module system of OCaml, which in turn is based on the module system of standard ML. However, we're not going to make very interesting use of the module system in this 3 days, certainly. Not very interesting use in the whole rest of the summer school, and you don't really need to know anything about how to use the module system. You just need to recognize that when you see the keyword module foo, from then on until you see end foo, we're now in a sub namespace where from the outside after the end, you have to say foo dot something instead of just something. And the reason we introduce them is to avoid polluting the top level namespace for things like natural numbers, which in Coq have a little bit of magic special syntax that doesn't work if you define your own. So here we are defining our own natural numbers, but then we're going to close the playground and go back to the standard library ones, which are defined just the same, except for the tiny little bit of extra magic. The extra magic I have to apologize for because it's a little bit confusing. I would like, and I think the Coq developers have promised that in some fairly not too far in the future version of Coq, there's going to be a way to define your own magic just the same as you can in the standard library. The fact that I have to say there's anything magical about natural numbers is very confusing, especially for people coming really fresh to the whole idea of these data type declarations and so on. So the way I'll say it to you is, there is absolutely nothing special about the natural numbers that are defined in the standard library, except that when they get printed out in Arabic notation instead of SSSSSO. And conversely, you can type Arabic notation, and that will get parsed into sequences of S followed by O. Okay, the more interesting, the deeper thing about this definition is that it is the first definition that is properly inductive. That is, the first one where the type that we're defining appears as an argument to one of the constructors. And that means that the set of trees that this definition picks out is an infinite set. They are all very tall and narrow trees, consisting of lots of S's with an O at the bottom, and you can see that from the type. Okay. And here are the Arabic numerals. Nothing too surprising about it. It's really just a hack in the parser and printer. Okay. Now that we have properly inductive data types, we need properly recursive function definitions, and we get those by replacing the keyword definition with the keyword fixed point. And then we can define things like, is this number even? We can define multiply, subtraction, etc. One slightly interesting thing about this definition is that here we're pattern matching against pairs of numbers. And in the patterns, correspondingly, we have pairs of patterns. Okay, and we can introduce the usual plus, minus, times symbols to make arithmetic expressions over natural numbers easier to read. All right. Oh, I see a question. Thank you so much. I see two questions. Wow. Okay, excellent. Thank you.
From the point of view of using any kind of computation in Coq, isn't it slightly problematic that the definition of natural is unary rather than binary? I understand that it's very useful for proving theorems, but if you are going to represent anything in memory that is not, if you want to write any non-trivial theorem involving integers and you take the wrong canonical representation, it will make your proofs very inefficient.
This is very true, and let me repeat the question because this is getting recorded. The question is, isn't this might be fine, this representation of numbers for proving things? In fact, I agree, it is fine for proving lots of things, but wouldn't it be terribly inefficient if you actually tried to compute over these numbers? And the answer is yes, it would. And so when people use Coq for writing programs that they intend to extract and use for real computation, they will do one of two things. Sometimes people just write their program using natural numbers, but then they tell the extraction machinery, whenever you see nat, please map it to, say, the Haskell big integer type, or indeed the Haskell word size integer type. And that is a perfectly legitimate thing to do. People do that very commonly. A different thing you can do, though, is you can define in Coq your arbitrary size binary numbers or your fixed size binary numbers, and then extract those in a smarter way. And that will even speed up computations within Coq, which is often a good thing. So the Coq standard library and a lot of user-contributed libraries include many different representations of numbers which are useful in various circumstances. We will only use nat for the next few days, but you'll see some of the others over the next 2 weeks. Another question.
Previous slide, please.
Previous slide.
There are quoting marks there. When you should use?
Yeah, so when do you need to use quote marks with the notation? So my system is, I always put quote marks around the whole thing that I'm defining. And then if there are symbols in there, they will be treated as part of the syntax automatically. If you want to have keywords in there, then you need single quotes inside of the double quotes around your keyword symbols.
Okay, thanks. So you define the associativity here, but back on the OR, there was no statement about associativity.
Right.
But then you had a compound OR, and it knew how to do the associativity.
Okay, so what about these associativity things? the observation is that here we're explicitly declaring the associativity, and when we defined OR, we did not. So when we defined OR, we were getting the default associativity, which I guess must be, well, it doesn't matter with OR, does it? It only matters with minus, really. That's the one that you have to be careful of. Plus and times and or and are commutative and associative anyway. So, so for minus, it is important that we say left associativity. And then these levels have to do with parsing. They have to do with the precedence of parsing. And this is all a little bit complicated. You can look it up in the Coq reference manual if you really care, or if you're defining your own new notations, which you will do eventually. But for the next few days, you don't need to worry about it. We'll define the ones that you need. Other questions? Let's go on. Okay, here's the less than function. So what? Here are proofs. We've seen proofs already, actually. We wrote little proofs of our unit tests. But they were kind of ridiculously simple proofs because there was nothing abstract, there was nothing quantified about the claims that we were making, so we could evaluate the truth of those claims just by simplifying. So this brings us to the other half of Coq. So Coq you can think of as a combination of two things. This functional language, Galena, and then a whole set of tactics, a tactic language that is used for guiding a stateful proof checker through the steps of validating claims that we make. So we can write down theorems, and then the keyword proof signals to the top level that now we're going into a mode where we're checking a claim that we've made. Each command that we then give, they're called tactics, should be thought of as an imperative command. So although Coq's programming language is functional, its tactic language is very imperative. So we're guiding this, we're manipulating the state of the proof checker to gradually knock out all of the goals that have been raised during the checking of this proof. And when we get to 0, then the proof is checked, and we can say QED. Now, in a day or two, we'll talk some more about the fact that actually those two sides of the Coq universe are not really so different as the way that we're talking about it now. But even so, it's a useful fiction, and it is the way that people think about getting work done in Coq most of the time. So let's maintain that fiction for now. Okay, so checking the time. I'm just going to keep blitzing on forward and let people ask questions. So we have very simple proofs. The only interesting thing we're introducing is the intros keyword that allows us to move quantifiers from the goal statement into the premises of the proof, into the hypotheses. Let's see. Okay, and now we have the rewrite tactic, which says take an equality that we already know and take a goal statement that involves something that you find on one or the other side of that equality and rewrite it, replacing that one by the other side. And rewrite can be used in both directions. So the default is left to right, but if you say rewrite arrow going left something, then the equality something, then the right-hand side of the something equality will be replaced by the left-hand side in the goal. Rewrite can be used not only with hypotheses from the current context, that is, hypotheses that we've introduced in the statement of the theorem that we're trying to prove right now, but also named things that are that we put in the context by naming and proving theorems earlier on. Next tactic is called destruct. And this is the tactic that we use for case analysis. So if we have something in the context that says, say, B is a Boolean, and we need to do reasoning by cases. Is it true? Then you think about it this way, and is it false? Then you need this other way of reasoning. We split the current goal into a case for true and a case for false, or if we destruct a number, a case for 0 and a case for successor of something, by saying destruct of the thing in the context. And this is also the place where we introduce the notion of bullets for structuring proofs that involve many sub-goals. You're going to develop your own habits about how pedantic to be about inserting bullets. I find that if I know that there's going to be a destruct, and then each case is just going to take a couple of little tactics, and then it's going to go away, people often ignore putting in the bullets for those sub-goals, and it's probably fine, but it's really easy to get confused. So as you're starting out, I recommend putting in all possible bullets. Every time you see that, that a tactic has generated multiple sub-goals, put in bullets. And then if you find that that's too annoying and too many bullets, and you don't want to do it later on, you can leave them out. It also depends on, sometimes you're working in a more exploratory mode, just trying to find out as fast as possible if something is true. Sometimes you've established that something is true, and now you want to go back and make your proof script more robust. That will often involve not just tidying it and putting in comments and whatever, but also introducing some automation. And trying to crunch it down so that if the definitions change a little bit, the proof will still execute. And that's something that we'll come to later on in this tutorial. Not today. Question?
Yes. If you have a case that's vacuous, how do you deal with that? Like, or a case that's not actually feasible? Because I've tended to get stuck there.
Excellent question. So what if you do a destruct and you wind up with some vacuous or nonsensical cases? That often happens. It's very common in paper proofs also. And in a paper proof, you would just say this can't happen. But if you unpack that a little bit, generally it can't happen because there's an explicit contradiction now someplace in the hypotheses. Right? So by doing the destruct, you've somehow, in one branch, introduced a hypothesis that black is white. And you need a way now of kind of getting the juice out of that contradiction to prove the goal. The way that the tactic that does that is inversion, or often destruct will do it. So and we'll come back to that. So save that question for a little while. But destruct or inversion is the short answer. Other questions? Okay. All right. We can nest bullets, and if you run out of bullets, if you get very deeply nested, if you find yourself running out of bullets very often, it's probably a sign that that you need to take some fact that you're establishing very laboriously in the middle of the proof and break it out as a separate lemma. So usually 3 levels of bullets is really plenty. Occasionally, you will need to go much deeper, and then you can use curly braces that kind of reset the bullet nesting. All right. And then one last thing is that, which we use a lot, is this notion of intros patterns. So destruct, I didn't say it explicitly, but you've read it in the chapter. Destruct takes a pattern in general, destruct takes a pattern that says what names should be given to the variables that are being introduced to represent the sub-expressions of the tree that you're destructing. So the destruct just takes the top-level constructor and considers all the possible cases. In cases where that constructor may have taken an argument, like with Nat, the successor, you need a name for the subtree, and it will be introduced automatically for you if you don't use an as pattern, and it will usually not be a very nice name. So Coq tries to be a little smart, and you could argue that its choices are not pessimal, but they're not optimal either generally. So, so it's good practice to introduce your own names. And in fact, this is probably an example of a bad usage. This is a case where we're destructing a variable y, and it appears to be from some type that has two constructors. The first constructor doesn't have any arguments, so the left-hand side of the vertical bar, we don't need any variable names. And the right-hand side, we've reused the name y for the name of the sub expression. And I actually often find that confusing myself. So if I were fixing this, I would add in a prime on those y's, the second and third ones. Okay. All right, and that's the end of the basics chapter. Any last questions? Please.
So in case we would like to discuss more modules, how to use them and something happening with the existing modules, whom should we talk to?
Who should you talk to about how to use modules? So the best place for information about Coq that isn't in the Software Foundations materials is Adam Chapala's book. And the best place after that is the Coq reference manual. So the Coq reference manual, those of you that have already had a look, you will see that it could use some work. It's been kind of, various bits of it have been written by various overworked and underpaid grad students and professors over the last 30 years. And it kind of shows it. So in the last round, the Coq team is aware of this. In the last round of upgrades to Coq, the manual was moved from its clunky old LaTeX version to a spiffy new Sphinx version that generates nicer looking HTML and that is easier to for community members to edit. And then the plan is to actually make it read better as well. This is a good moment for me to make another request to you. All of you are in a rare position as members of the Coq community. So you are now members of the Coq community, but you don't know too much about Coq yet. That's a golden position. It's only going to last for a few days. So my request to you is, if you find yourself looking at the reference manual or indeed looking at anything in Software Foundations or any place else, please notice when there are things that you don't understand or that don't make sense or that could be said better, and either tell somebody or, better yet, write it better yourself and submit a pull request. The Coq team is very happy to have pull requests on the documentation, and it's a very good way to get involved in contributing to Coq without the hairiness of getting involved in the implementation. So, so please take it on yourselves to help improve the materials that we share. Please.
Particularly at last year's event, some people got together and started writing a lot of new
oh yes, I should say that. The reason that the documentation is now in Sphinx instead of the bad old LaTeX version is because of last year's summer school. Somebody at the summer school said, oh, I see something that we could do to really help move the ball in the Coq community, and it's going to take a lot of effort, so we should do it together. And they assembled about 20 people from the summer school to sit down and do the translation of the documentation. Please.
I have a question about the Coq IDE. I done a little bit research for the new Coq, and there is a proof state panel which show the current subcores and refresh in real time. And when I use the Coq IDE, I think that left upper panel is the subcore panel, is it? But there is nothing displayed on my computer. Is it common to everyone or?
So this is a question about Coq IDE, and the question is, it seems that the panel where the subgoals look like they should appear isn't actually displaying anything. That sounds like a question to take up with somebody during the break. But my experience, I don't use Coq IDE very much, but my experience using Proof General is that the subgoal panel is only displayed when it's in the middle of, when the cursor is actually in the middle of a proof that's halfway checked. So it may be that it's correctly blank, and you just need to move to a different part of the file. Okay, other last questions? Good. Let's move on to induction. Okay, I'm going to skip this. Okay, separate compilation. Again, you've probably mostly encountered this already and solved it, but this will be the place where things will get messed up. This line will be the place where things will get messed up if you're having search path problems. And I'll just tell you my favorite way for solving them is the way that things are compiled if you do it directly from the IDE, either Coq IDE or Proof General, treats the paths a little bit differently and produces a different .vo file than if you say make at the command line. So if you see messages about, blah blah says basics, but something else has top.basics, try removing all the .vo files and starting again. If in your IDE you ask it to accept this line, it will automatically recompile the basics file for you if it needs to be recompiled. So just throwing away the .vo file and asking it to process this line will have the side effect of recompiling basics in the right way. Okay. Proof by induction. Obviously, once we have definitions by recursion, we need to prove things about them using induction. Once in a while, you can prove something about natural numbers using just a destruct, but not for very interesting function definitions. So almost always, you need to use induction. And here is the principle of induction for natural numbers. It says, if we have a proposition involving a number, so we have a proposition about a number n, and we want to show that this proposition, P, holds no matter what n is, we have to do two things. We have to show that P holds of 0, and we have to show that P holds of n prime under the assumption that it holds for, we have to show that it holds for successor of n prime under the assumption that it holds for n prime. If we can do those things, then it holds for all n. So this is exactly the natural number induction principle that everybody is familiar with from discrete math. The only difference in Coq is that it isn't a kind of special thing that's only for numbers. It's something that is generated every time you give an inductive definition. So the keyword inductive, when accepted by Coq, automatically generates an induction principle that for the natural numbers is exactly this, and for other structured data types like trees or whatever is the appropriate thing for that type. So every inductive definition comes with an induction principle, and we can access that induction principle in various ways, but the simplest one is using the induction tactic. So the induction tactic is like destruct. It's exactly like destruct, except that it binds one more thing in cases that are where the data type, the inductive declaration is properly inductive. That is, one of the arguments to a constructor is the type that's being inductively defined. Then we're going to get an extra variable, which by convention I usually call IH something something to remember that that this variable is representing the induction hypothesis. Okay, now I have a question for you. No, I'm going to answer it myself. I'm not going to do this one together in class because I want to get through all of these 3 chapters and we're running out of time. But I will gladly answer questions at any point. Okay. We can structure proofs in Coq in many ways. One simple way that's often useful is writing a quick lemma inside of a proof and immediately proving it right there and then going on to use it. So this tactic, assert, says, I want you to do 2 things. I want you to create a sub-goal asking me to prove this. And then once it's proved, I want you to give it the name H and allow me to use H in the rest of the proof. Actually, I might have said that backwards. Maybe the sub-goal of proving H comes second, and the use of H in the rest of the proof comes first. In any case, you get 2 sub-goals, one to prove H and the other assuming H. So it's just a way of splitting a proof into a subsidiary fact and a use of that fact. And I'm going to skip over that. Okay. A little discussion about formal proof versus informal proof. So informal proof is what we do on paper and what mathematicians do in textbooks and what computer scientists do in the papers that they write. And its purpose is similar to the purpose of a formal proof, but not exactly the same. So strictly speaking, the purpose of a formal proof is to get the proof checker to say yes. And you can interpret it as saying something about a mathematical truth, but really it's just a program that's driving the proof checker through a sequence of states and getting it to a state where it has no sub-goals. As such, a formal proof tends to be a rather low-level thing, just as a realization of some distributed protocol in C tends to include a lot of details that are important to get the thing to run, but that are not actually that germane to understanding the main functioning of the protocol in your mind. So proofs and programs can be used in different ways for different purposes. They can be used for establishing truth in the case of proofs. They can be used for creating behaviors in the case of programs. They can be used for communicating belief or instilling belief in another person in the case of proofs. And they can be used for communicating understanding in the case of programs. And these are related activities, but not the same. It's important to realize that because it's easy to fall into the trap of thinking that when you've proved something formally, you understand it, which isn't always the case, or even worse, that handing somebody a formal proof helps them understand something, which is typically not ever the case. So formal proofs always need to be accompanied by explanations, intuitions, comments, good naming, splitting things up into nice structures, and so on, all the same sorts of things that we do with informal proofs. Let's see, I wanted to say one more thing. Yes, this realization of the kind of sharp divide between formal and informal proofs came as somewhat of a disappointment to me about a couple of years after I wrote the first version of what became the Software Foundation series. So my idea originally, I had been teaching from an older textbook that I had written that only had paper proofs, and that covers a lot of the same material. I've been teaching that for many years, and I was frustrated with the fact that a lot of people coming to my course didn't understand how a proof worked, didn't understand how to think about proofs for one reason or another. And I really felt like I didn't have the energy or the number of TAs needed to help everybody with that problem. Just like, if we were teaching a course about history and people came not knowing how to structure sentences in English, it would be pretty hard to kind of help them with those grammatical problems at the same time as teaching them how to write papers about history. So the idea of Software Foundations, the original kind of rallying cry was 1 TA per student, and the TA is called Coq. I think that was a good idea, but it only worked about 80%. So I think Coq is good for teaching people how to think about proofs, but it's good for teaching people how to think about formal proofs, not how to think about informal proofs. Writing good informal proofs is a question of communication, it's a question of writing, it's a question of conveying understanding from one human mind to another. And that is just a different process from the hacking that's involved in getting formal proofs to work. So the point of that sermon is formal proofs are good and useful, but don't think that they're all there is to life. It's also important to learn how to abstract from those formal proofs and communicate ideas. And that's a kind of a separate process. All right. And that's the end of that chapter. Any questions? Okay. Last chapter for this morning, for this part of this morning, is lists. So we wouldn't get very far programming in any functional programming language or any other programming language without data structures. We've seen ways of defining numbers. Here are some more interesting ways of putting together structured data. So numbers were in some sense already a form of structured data because each number that isn't 0 has a number inside it. So you can think of a number as a list of S's. And indeed, that's a useful way to think of it. But we would like to have lists of other things. We would like to have pairs. We would like to have other data structures, trees, whatever. So here is a type of pairs. So this is a constructor that takes 2 arguments. And it's interesting as an inductive type because it only has 1 constructor. So every value of type natprod has the constructor pair sitting at the top. But of course, that pair can be applied to any 2 numbers, and that's what's interesting. So when we pattern match against a pair, there's only 1 clause in the pattern. And the interesting thing that we're doing is binding the variables in that pattern clause, which we can then use on the right-hand side. As for other things that we've defined, we can define notation for pairs. So we'll define the usual parenthesis with comma in the middle notation for pairs. And we can use it, interestingly, both on the right-hand sides and on the left-hand sides of pattern matches. So we can write pair syntax also in pair patterns, and that's quite useful for making things readable. All right. Here's a simple thing we would like to show about pairs, that every pair is equal to the pair of its first projection and its second projection. And this proof is very easy if we write the theorem in this kind of peculiar way. But a nicer way to write the theorem is this, that anything of type pair is equal to its own the pair of its own first and second projections. And this doesn't simplify, so reflexivity does not prove it. How do we prove it? With destruct. So once again, destruct is our friend. Okay, here going on from pairs to lists. So here is a properly inductive type of lists of natural numbers. It has a constructor nil and a constructor cons. The constructor cons takes a nat and a nat list. And we can have some familiar notation. We use double colon for the cons symbol because single colon, which would be more familiar for Haskellers, is used for type of in Coq. And we use square brackets. And by the way, we use semicolon instead of comma for separating the elements of a list. I don't know exactly why they made that decision early on, but that's the way it's done in Coq. And then with those things in hand, we can write some useful recursive functions over lists. And once again, this is completely familiar for those of you that are experienced functional programmers. So here is the repeat function that takes a number n and a count, which is the number of times to repeat it, and returns a list of that many copies. Here is the length function. Here is the append function. And here is some special syntax for it because we use it a lot. Here is head and tail. But here we run into a little discussion about about the fact that Coq is total. So the tail function looks exactly like the tail that we would write in ML or Haskell, but the head function has a default argument. So it has to take two arguments, the list that we're taking the head of and the thing to return if the list happens to be empty. We need that because in Haskell, you would just raise an exception here, but Coq doesn't have exceptions. Why doesn't it have exceptions? Because the functional language, as we're going to find out tomorrow or the next day, also has logical content. And so raising an exception would be kind of a funny thing to do in a logical sense. So we don't do it, please.
Are all your functions total in Coq?
All functions are total in Coq. Let me make one comment about that, and then I see one more question. So all functions are total in Coq. There are different ways that can be used to prove that a given function definition is total in Coq. The way that we'll use exclusively for the next couple of days is the simple way, which is Coq will automatically, so look here, this declaration, let's see, wait a minute, this is tail, so this is not interesting enough. Let's go back to length. So here we make a recursive call to length. How do we know that that recursive call will always terminate eventually? Because this t is a pattern variable that was obtained by pattern matching against the L that's the argument to the function that is in the same position as the t here. So it's just syntactically obvious that t must be a subtree of L. And this is exactly the reasoning process that Coq's termination checker does. There may sometimes be recursive functions that do always terminate, but that you can't see it by this kind of very simple sub-expression reasoning. And for that, Coq has more sophisticated facilities where you can attach a termination measure, which you later prove is actually decreasing. Okay, so I'm not going to show you that. I'm just letting you know that it's available for the time when you will get to eventually where you need to use it. But actually, the simple termination measure plus just learning to program in a style that it can recognize will get you very far. More questions? Yes, please.
The usual termination is done automatically by the Coq?
Yeah. So Coq is so when you're using the simple termination checker, the checking is completely automatic.
And if it's not automatic, then Coq will ask us to prove, or like we have to.
So what would happen? What would happen if we made a mistake? So for example, what would happen if we put L here instead of T? We would get an error message of the form, I can't show that that something is going down. And then we could switch to the other style. Other questions, please.
So between the slides, you were switching between fixed point and definition.
Yeah.
And fixed point is in particular for recursive functions. So why not just uniformly use fixed point in place of definition?
Okay, so I've been switching between definition and fixed point depending whether the thing I'm defining is really recursive or not. Could I just use fixed point everywhere? Yes, I could. Why not? Matter of style. I think if you want to use fixed point everywhere, nobody will object. It's adding a little bit of extra information to the person that's reading the code that says you don't need to bother looking for the recursive occurrence of this. Maybe it's a little bit OCaml versus Haskell style. So in Haskell, everything is naturally recursive. And in OCaml, things are not recursive unless you explicitly say. So I think that distinction percolated into, or was inherited by Coq. Other questions? Okay. All right. Let's ask you some questions. So do not submit any response when you have the answer. Raise your hand when you have the answer to this question in your mind. How many hands are up? A few hands going up. Okay, I'll give you another couple of seconds. Doesn't matter if you're wrong. Okay, many hands are up. Who wants to say? Too many hands up. You say.
Okay, does this like take the list and then append to that the list or the tail of that list and so on and so forth?
Ish. Let's try again.
So if you give a number, then it gives you a list back from 0 to n-1.
Yeah. So you give it a number. You can see that you give it a number from the first line, and it's going to give you back a list of numbers, and that list will contain the numbers 0 to n-1.
I think so.
N to 1. In which order?
Descending.
Descending. So we'll have n at the front and then n-1 and so on, but it won't have 0 at the end because we returned nil here rather than a singleton 0 list.
Yes, but if you call it with 1, if you put a 0,
Let's check. If you call it with 1, what will you get back? A list containing just 1.
a 0. A 0. Because 1 is S0, and if you put the 0 in front of 0.
I don't think so. Okay, so if you call it with 1, what will happen? Let's work it through.
Okay, sorry.
Yeah, so you give it n, it matches n. So you give it 1, the pattern matches 1, 1 is successor of 0, so it puts 1 cons foo of 0.
Okay, so 1 to 1.
And foo of 0 is nil.
Okay, sorry.
No need to apologize. Being participating and getting it wrong is better than not playing. Okay, so all of this is reasoning about lists. All of this is defining programs using lists. Now we want to reason about those programs. And what tactics do we need? Well, all of the ones that we've already used are useful. In particular, for properly recursive definitions about lists, we will want induction. Okay, so sometimes you can do proofs about lists just using simplification if the thing you're proving is particularly trivial. Sometimes you need case analysis that you can get just using destruct. But mostly you need induction. So here, for example, is the associative property for the append function, and we prove it by induction on what? Well, we have 3 lists here, so in principle there are 3 things we could do induction on. How do we know which one to use?
Look at the definition of the function and see on which one it calls it here.
Indeed. So the smart answer is we look at the definition of the function and we see on which argument is it making a recursive call. The less smart answer, which is the one that I might give if it were late at night and I were in the middle of hacking on this, is try it and see. So And in general, the smart answer may require arbitrary amounts of smartness. So the main difficulty, in fact, in doing many proofs in Coq, as in any other kind of proofs on paper or whatever, is figuring out on what to do the induction, and often what should the induction hypothesis look like. So this is where creativity is involved, not just hacking. So, so it certainly seems that doing induction on L3 would not be very useful, because L3 is always going to be the second argument to append everywhere here. And the second argument to append is never investigated by the definition of append. It's only the first argument that it uses. So it's got to be either L1 or L2, and in this case, L1 is a good guess. So we do induction on L1. Once again, in the nil case, we don't need to bind anything. In the cons case, we bind the number at the head, we bind the rest of the list, and we bind a variable standing for the induction hypothesis. In the nil case, it's easy, as base cases often are. And in the cons case, we basically just use the induction hypothesis, and we're done. Okay, here is list reverse. And now, here is a proof that I think I won't bother going through with you, that actually, this is in some sense one of the first interesting theorems that we've had to prove. There were a couple of interesting theorems about numbers, but not too many interesting theorems yet. It's just been finger exercises. But this theorem is kind of interesting. It says if you, it tells you a relation between the length function and the reverse function. Namely, reverse doesn't change length. Length is invariant under reverse. And the proof is pretty simple. Except that you need a subsidiary lemma. So if we simply try to prove it directly, we get into a stuck state where the induction hypothesis just isn't quite enough. So what you need is, because reverse is defined in terms of append, you need a lemma relating length and append. And once you get to this point in the proof and notice why you're stuck, it's kind of obvious, and you say, okay, well, I could have realized that beforehand, but it doesn't matter because I can just back up and do it. So you state this and prove it. The proof is not hard. And then with that proof in hand, we can go back to the first one and get all the way through the proof. Okay, let's see. I'm going to skip over those and talk about options. So we've seen already an awkward situation with the list head operation, where when the list is empty, we have to provide a default argument. But the default argument is a number, and the thing that it's supposed to return anyway is also a number. So how do we distinguish between, as a user of the head function, how do we distinguish between the case where the list was empty and we got back a bogus number versus the list was non-empty and we got back its head? Same thing can happen with functions like inth. So inth is intended to extract the number at a certain index in a list of numbers. And here we haven't bothered with a default argument. We could, but we've written it in a different bad way where it just returns some default. It returns 42 if the list doesn't have enough elements. And I think I don't need to convince you that this is bad. So what could we do that's good? Well, we should introduce, in most programming languages, the good thing to do would be raise an exception. In Coq, we don't have exceptions, so instead we return a value that says it wasn't there. And the convention, which again Coq inherits from ML, is a type called option. In Haskell, it's called maybe. And it has constructors sum and none. You may wonder, why are sum and none capitalized here when all of the constructors, or most of the constructors so far, have not been capitalized? There really isn't any rhyme or reason to what gets capitalized and what doesn't get capitalized in Coq. And the reason is that because Coq has such a powerful type system, we end up writing things at the type level that do computation, and things at the value level that take types as arguments, and things at the type level that takes values as arguments, and all of the kind of simple rules that you would think of to keep the layers distinct in other languages don't really apply here, because the layers are intentionally mixed up. So some people have conventions. There's a general convention that things with capital letters are either constructors or types. Types are generally written with capital letters, but not always. And so it's really just kind of a mess. But at the end of the day, it doesn't matter that much. Life goes on. Okay, so nat option is a type with two constructors. The none constructor doesn't take any arguments. It just says there's no data here. The sum constructor takes a nat as an argument. So it says there is data here, and here it is. And now we can write int in a better way, returning a nat option instead of a nat. So in the nil case, we return none. And in the case where we haven't found it yet, where we haven't recursed far enough, we just make a recursive call. And in the case where we did find it, we return sum. And then when we call nth error, we're going to need to pattern match on the result to find out whether the result it gave us back was a good one or not. And this is a good time to mention the fact that Coq has an if syntax that can be used instead of pattern matching when the thing you're pattern matching on has exactly two constructors. But wait, we defined our own Booleans, so how does the built-in if know that which is true and which is false? The answer is if works on constructors with on data types with two constructors, and it considers that the first one represents true and the second one represents false. So the fact that TRUE gets us to the first branch of true is completely incidental. It's only the fact that it was the first constructor that we defined in the Boolean definition.
What if my constructors were not nullary?
I'm sorry, what if the constructors are not nullary? Excellent question. So you can apply it to, for example, numbers, I believe. And in that case, the extra information will just get thrown away. All right. Yes?
So is this like a macro for the match?
It's a macro for the match. It's just convenience. Okay, we can use that, everything we've defined so far, to do a little bit of programming and define a type that's going to be useful a lot later on, which is the type of identifiers. So this is a trick that's often played in OCaml and Haskell, where we define a new type with just one constructor, which takes just one argument. So you might think, why is that a useful thing to do? Because the members of that type are exactly isomorphic to the members of the original type. And that's exactly the point. So they are isomorphic, they're not the same as, and the type checker will not allow you to mix them. So every ID contains a number, but IDs are not numbers. And that means that, that if you accidentally write a function that wants an ID and pass it a number, you will get a complaint from the type checker. And that can often be a good thing. We will use them as we go along for things like Well, we will use something similar for the type of variables in programs that we represent as Coq data structures. Okay, now, we already wrote an equality test for natural numbers, but as I just said, you can't mix the types. So if we want to test for equality of IDs, we're going to have to write our own definition of an equality test for IDs. Of course, it's easy to write using pattern matching. There it is. Now we can define a type of partial maps. So a partial map is basically a list. In Lisp or Scheme, we would call it an association list. So a partial map could be empty, or it can be a record containing an identifier that is a key, a number that key maps to, and a partial map, which is kind of the rest of the bindings. And then we can define an update function that takes a partial map, an identifier, and a value for that identifier, and adds a new record to the front of the partial map that you gave it, which will, if that identifier, if that key happened already to be bound, it will now be shadowed. We're not actually throwing it away, so this isn't the most efficient update function that you could imagine, but it is correct in terms of behavior. And we can write a lookup function called find that attempts to find a key in a partial map, returning, of course, an option because it may not be there. Okay, here's a question for you. Is this theorem true or false? And please raise your hand when you know the answer, or when you're sure that you're not sure. Okay, some hands going up. So I am for the moment asking for people just to indicate when they've thought about it enough. And now that that has happened, what is the answer? So who thinks they know?
It's true.
It is true. So if you update a map and then look up the very key that you just added to the map or shadowed in the map, what you will get back will be the value that you put in. What about this one? I'll just give you a second to think about it. Okay, who thinks they know?
This should be true as well, because the first step of executing find will simply be the cursor invocation.
Yeah, so this is true as well, I agree, because the hypothesis that x is not equal to y is telling us that the top invocation of find will discover that the front thing on the updated map is not what we're looking for, and then make a recursive call, which is just the right-hand side of the equality. So whatever that gives us will be what we get back. Okay, and that is the end, and it's coffee time.